In this video, we're going to take a quick look at systems of equations. Now, there is a lot that we can talk about when it comes to systems of equations, but since we're limited in time, we're going to focus on just a few details. The first thing that's important to recognize is that any system of equations, which is just a group of equations that we want to hold true simultaneously, can be written as a matrix vector product, of course, as long as the equations are linear in nature, where the matrix here contains the coefficients from each equation. So the first row is 0, 2, 3, corresponding to 0, 2, and 3. And the vector is the vector of unknowns. And of course, there's a right-hand side vector here as well. So a system of equations can be written as a matrix equation. In some applications, a system of equations will have an exact solution. This is rare. More often, there's two situations where systems of equations present themselves in analytics. The first is in optimization. And when we're in optimization, they're not necessarily systems of equations, meaning there's an equal sign there. There's often a constraint involved. So we need some linear combination to be less than or equal to some value or greater than or equal to some value. This would be referencing like labor constraints. We can only have employees work a certain number of hours, or input constraints. We only have a certain amount of capital to put to work at any one time. And so when you have that type of system where you're looking at a set of constraints, there's often infinitely many solutions within those constraints. And so your goal is to look within the constraints to find some optimal solution where you're trying to optimize some other quantity like profit. So within the constraints of my business, how do I optimize profit? This third bullet point is the situation that we find ourselves in for linear regression. And this is where there's no exact solution. And what we do then is introduce an error term and try to minimize it. Let me take you through an example with some data and show you how regression analysis can be seen as a system of equations. Here I have 6 observations. Let's say that they are packages and I have their weight, their width, and their length, and then the time it took to review that package. And my hypothesis is that the time it takes to review is some function of the weight, width, and length. Now, when I write this equation, I'm calling it a hypothesis because I haven't proven that these things are related in any way. But when I write this equation, what I'm really saying is that I want this equation to be true for each observation in my data. So for instance, I want observation 1, which has a time value of 10.11, to be equal to beta 0 plus beta 1 times weight. Of course, the weight of observation 1 is 3. So I've just put in the actual data points for the first observation into the equation. And so I want this equation to be true, and I also want it to be true for the third observation. Of course, I'm only skipping the second to show 2 examples. I want this to be true for every observation in my data. So what that means is that when I write this regression equation, I'm really saying that I want time to be a linear combination of, well, an intercept column that gives me my beta 0s, the weight column, width, and length column. Now, I know from experience that I won't be able to do this. I'm not going to be able to reach equality here. My data does not lie on a straight line or straight surface. So I have to understand that this will be approximately equal to, and I add in an error term. But what I'm really trying to get at here is that the regression equation is a matrix vector product, where I have a matrix X, typically called my design matrix, that contains all of my data and a column of ones for an intercept. Of course, if I had any categorical attributes, they would be made into dummy variables in the design matrix. And I also have a vector of target values, or here the time. And I'm adding in a vector of residuals, because I know that I'm going to have some error. Of course, the beta hats here are what I'm trying to find. I'm trying to find the beta hats that will minimize the error. Okay, so if I start with this system of equations, y equals x beta, of course I know it to have no solutions. It's what we call an inconsistent system because it has no exact solution. What we want to do is find the beta values that get the modeled values, or the predicted values, the y hats, which would be created by x times beta, on the right of this equation, as close as possible to the true values on the left. And we do this by minimizing squared error. So we minimize the sum of the squared residuals. Of course, again, the residual vector is created by subtracting those predicted values from the actual values. So if we keep that in mind, there are some equivalent ways to write this. We can also write that we want to find the beta that minimizes y minus x beta transpose y minus x beta. Now, why? Well, because when we take a vector, inner product with itself, remember, every vector is a column vector. So when I put the transpose, I make this a row. This is a row containing the residuals. This is a column containing the residuals. And when I do that inner product, the result is the sum of squares. Another way to write this is to minimize, find the beta that minimizes the 2 norm of that residual vector, or y minus x beta squared. Now, it's important that I show you these different ways to write squared error because they're commonly used in the literature. So it's good to be familiar with them. Now, I haven't talked about this norm notation yet in the 90-minute primer, and that will be coming soon. So this is something that we can revisit after a few videos. But the next question on your mind is, okay, well then how do I find the betas that minimize these expressions, that minimize the squared residuals? Well, it turns out we solve a related system of equations known as the normal equations. The normal equations take that same system, x beta equals y, and multiply both sides by x transpose. We haven't yet discovered the machinery of why we need to do this. You can do it with calculus on this previous slide. If you actually work out this expression, take the derivative and set it equal to 0. For those of you who have taken calculus, you recall that's how you minimize or maximize something. You will arrive at the normal equations. If you haven't taken calculus, that's just fine. Don't worry about it. We won't be using much of it here. So I give you the normal equations, the solution of which will be the least squares solution. Now, the nice thing about this is that as long as that matrix X is full rank, which just means that there's no perfect multicollinearity, no perfect linear dependencies between the columns. As long as that's true, this matrix X transpose X has an inverse. And so that means that this system has an exact solution. We just multiply both sides of the equation by X transpose X inverse. When I do that on the left, I'm left with just beta. Here I've gone ahead and marked it as beta hat because I know it's my solution. And when I multiply that on the right, it just stays as this rather messy form X transpose X inverse, X transpose Y. And that will give us the least squares solution to the regression system. I will give you another way to view regression when we get to the subject of orthogonal projection in the second week of class. For now, what I want you to know is that we're done talking about regression in linear algebra class. From now on, aside from that one time that I'll revisit it, our focus is on unsupervised problems. Unsupervised means that we don't have a target variable. There's nothing we're trying to predict. Or we may be trying to predict the future in some way, but we don't have a target variable that we can train a model with. And the reason why I have this slide is because it's very common for students as we get into the linear algebra mindset in the first 2-3 weeks of class, for them to try to connect the dots on what we're talking about to what they already know well, which is regression. And that's problematic because we're not dealing in a world of regression. We're dealing in a world where there is no why, nothing that we're trying to predict. And so I really want students to learn to not try to draw those connections as we go through. And I'll remind you about this as we get there. Okay, next video, we'll talk about norms, distances, and similarities.